This is the final installment of the Battleships-Noir series. In this video, we're going to look at integrating our Noir proofs into a front-end application. We'll show where they wrap into the React code and how they connect to the smart contracts, and also show how web workers can be used to run the TypeScript libraries that Aztec provides through a WebAssembly file. But let's go ahead and get started. So looking at the front-end repository, this is a React application created using Create React App. And we actually have to take a few things into consideration to run the Aztec TypeScript libraries here. These are npm packages that are native to a node context. So in order to run them in a browser, we have to convert the underlying packages to a form that is friendly to the browser. In earlier React versions, this is React Scripts 5, but in earlier React Scripts versions, we had an automatic process called Polyfilling, and this is a way of converting those underlying node packages into a browser-friendly form. But in React Scripts 5 and above, we have to take this process upon ourselves, and we have a few ways of doing this. So number one, we could choose to eject the app, and what this does is it will expose all of the underlying dependencies in the React application, bring them into the package.json, and also expose the configuration files for Webpack, etc., that you'd need to specify manual polyfills. And we actually have a few packages that can make this easier. There is React App Rewired and also Craco. And what these npm packages allow us to do is they allow us to specify configuration files to override the React app without actually ejecting. So in the case of Craco, which we use in this repository, we just have to specify a craco.config.js file. And here we specify our polyfills and other configuration overrides. And once we have that file implemented, all we have to do to run the React app with those overrides is switch out where React scripts would go in our scripts here. Instead of React script start, it would be Craco start, Craco build, Craco test, etc. And I definitely recommend this method over ejecting because it maintains a much cleaner code base and is much easier to demonstrate and follow along with. And then real quick before jumping into the bulk of the code, just want to highlight that another consideration we have to take before running these packages in a front-end context is we have to include the WebAssembly file representation of these packages. And these can be found once we do yarn install or npm install the Aztec packages. We just have to dig inside of them and we'll be able to locate them. But a way to do this more efficiently that we set up is in the main Battleships-Noir repository. We have a script that will expose these files, automatically go into the node packages, retrieve them, and also generate a bufferized version of the Acer for a specific circuit and a bufferized version of the circuit. Because all of this is needed in order to run the circuits in the browser, which we'll get to shortly. But let's go ahead and start jumping into the code and let's see where these proofs plug in. So looking at the build board view, we start off with an array of ships. You'll notice each ship has an image associated with it, a name, a length, and then a sections array. And these are all initially empty, but we fill this when we place our ships when starting a new game or placing our ships before joining a game. So just going to the front end real quick, place your ships, then explain what's happening. So the way the coordinate system works is indexed from 0 in the top left to 99 in the bottom right. And it's the sum of the x coordinate and the y coordinate times 10. So this is going to be, or represent x coordinate 0, y coordinate 0, x coordinate 9, y coordinate 0, y coordinate 9, x coordinate 0, and then y coordinate 9, x coordinate 9 in the bottom right. But this isn't the form we want for the ships when we pass it into the proof. So just showing real quick, this is our state array for when we place ships. Once all the ships are placed, we can then start a game. And what happens then is we enter the start game function. And we'll notice real quick, If there is an ID associated with the game, we infer that that is a pre-existing game. So this will actually be treated as a join and not a game creation. As we can see here, we'll call the join game function in the smart contract. But we're focused on the create game implementation of this. So what we need to do first is, well, we'll scroll up here real quick. So what we do for both joining a game and creating a game is we first convert these ships to a format where the proof can read it. So we look at where the head of the ship is, the head being the furthest to the left or furthest to the top, depending what orientation. So you can see head is 1A right now, and now head is 4I. We take that and we calculate the x coordinate from it by getting the remainder of it divided by 10, the y coordinate by dividing that value by 10 and rounding to the floor, and then finally the orientation of that ship. If it's an x orientation that is horizontal like this, then we'll assign it a value of 0, and if it's y, we'll assign it a value of 1. And then finally we push these values to the board array. And this is going to be a 2D array with the inner arrays being of length 3 and each inner array representing a ship, the x, y, and z coordinate. We then pass this board into the board proof function. And in here, we first create a ship hash. And just showing this off real quick, it's exactly like we do it in the main repository implementation. We just import the Brandenburg WebAssembly class, initialize a new Brandenburg WebAssembly, and then import the single Peterson class so we can access the Peterson hash function, and then just convert this board array into a Peterson hash. And once we have that hash, as shown in this function here, we have to flatten the array first. So right now it's a 2D representation, but we want to convert it to a 1D array because that is currently what Noir supports right now. Finally, from here, we will then go ahead and jump into the generate proof function. So this function is a function that can take in an arbitrary proof type. In this case, obviously for our application, we only have a board and a shot proof, but we specified that when calling this function, as well as the input for the proof. And we have two types. We have a board ABI type and a shot ABI type, corresponding to the public and private inputs for a specific proof. And actually, before moving on in this function, let's just go up here real quick. We also have a mapping that specifies the proof name and then maps that to the associated files, the Acer file for that circuit and the circuit file for that circuit. Another important thing we need to know when running proofs in the front end is the size of the circuit. And we can learn this from running Nargo compile like we did in a previous video. And also there is a way to get the circuit size of TypeScript as well. But for our use case here in the front end, this needs to be known ahead of time. But moving on to this function, the first step is to initialize the Noir WebAssembly package, and that's imported from Noir WebAssembly. Actually, we could probably simplify this and just do this. Oops. There we go. But yeah, no, we initialize this, and then the next step is to fetch the circuit file associated with the specific proof. So if we were using Node, we could use the file system package, but in React, the best way to fetch an arbitrary file type is using the fetch method, even though it is located in the same application, so not necessarily async. We then convert that response to a buffer and then convert it to a uint8 array, and then we have a usable circuit. The same is done for the Acer file. We get the response, convert it to a buffer, convert it into a uint8 array, and then we can convert it into readable Acer by using the Acer from bytes function imported from Noir WebAssembly. Once we have that step complete, then we move on to setting up the prover in the front end, and we have a function here to be able to do that. There's a lot going on in this function, so we're not going to dive into every part. Just walking through real quick, we load in a common reference string based on the size of the circuit. Then we initialize the Brandenburg WebAssembly class, and then that is passed into a worker pool. And worker pool is imported from Brandenburg as well. And this is a pool of web workers that are used to execute WebAssembly code. A web worker is a way of executing JavaScript that is not on the main thread of execution. So for expensive processes, this can be a good choice so it doesn't disrupt the main flow of events. We'll dig into that more in the part where we implement our own for the Aztec backend package. But moving on, we take this initialized worker pool and put it into the pooled Pippinger class. And Pippinger is an algorithm we're not going to dive into too much here. And we also take that same worker pool and put it into a pooled fast Fourier transform class. We then initialize the fast Fourier transform with a circuit size and initialize Pippinger with the common reference string data. Once we have all of this, we pass it into a prover, which is imported from Brandenburg as well, and then pass this into a custom standard example prover class. And from here, then we actually initialize the circuit definition. As we can see here, a bunch of calls made by the web worker. And then finally, compute the proving key with the common reference string, and then await all of the promises to resolve. And then finally, going back here, we have our prover. And this function was taken from the Hello Noir UI repository. You can find it if you look at the Awesome Noir resource section on GitHub, and we'll also link to it at the bottom of this video, as it was instrumental in getting this front-end implementation to work. But in the next step, we initialize a web worker for the Aztec backend. And as mentioned before, web workers are a way of moving an expensive computation from the main thread to a background process. And in the specific case of the Aztec backend, we want to be able to compute a witness for a circuit in the browser. And in most cases, this will work without a web worker, but in circuits with larger inputs or ABIs, we'll run into an error where it says we can't run a WebAssembly module greater than 4 kilobytes in size in the main thread. So for this reason, we need to use a web worker for this specific implementation. And for this web worker, we want to create two promises. We want to create an error promise in the event of an error and a result promise in the result of a successful execution. And what we're inputting a URL to the Aztec WebAssembly package. We're putting the Acer file for the proof in, as well as the input or the ABI of the circuit, in other words. And just jumping into the worker real quick, we can see this onMessage function. Get all of our data here, convert it to hex, and then we initialize the Aztec backend with the path to the WebAssembly file, and then finally compute the witness, which is imported from the Aztec backend as well. And that takes the Acer and the hexified values of our input. Next, we get the witness. It's either going to resolve to the error promise or the result promise, depending on the success of the execution. And then finally, with this witness, we can use the create proof function taken from our prover, and then finally return the proof. If we have the proof, we pass it to the smart contract along with the ship hash, down to the start game function again. Real quick, we can either in this function join a game or create a game based on whether a game ID exists in the query parameters. So if ID, we join a game. If no ID, then we create a game. We take the ship hash and the proof and we pass it into the transaction function, which calls our smart contract. And then finally, at the end, we store the ship state in local storage. So we're able to fetch our ships again if we were to get disconnected, leave the site. And then we navigate to the active game location. So we'll just go ahead, demonstrate that here again, like we did in the fourth video. All right, and here we are in the game. And we're not going to bother demonstrating the same functionality again for joining a game. We'll just go to another active game with 2 players already and demonstrate the shop functionality there. But on that note, let's go ahead and go to the game view and actually explore where that proof is implemented. So scrolling to the bottom of the file, we have our own board and we have an opponent board. And we look at the game view, obviously opponent board on the left, our board on the right. And similar to when we place our ships in the new game view, when we select a tile, all tiles are going to be arranged from index 0 to 99. So going into the opponent board, can see here we have a state variable called selected tile that will be assigned the tile we click, and then hover tile is any tile we hover over. Then we see this crosshair. But going down, when we finally click fire, we will call this handle shot function. We will get the x coordinate by getting the remainder of selected tile divided by 10, and we will get the y coordinate by dividing selected tile by 10 and rounding it to the floor. We will then increment whose turn it is and take the shot. And when we click take shot, that will take us up into the parent component in the game view. And let's search for it real quick. And here's the function right here. So we will then add this shot to our state array for shots, and if it's the first shot, we will not generate a proof for it, because remember, we're generating proofs when we report the previous shot back. And anything that is the first shot, obviously nothing before it to report. So we will skip the proof generation phase and go directly to the shot transaction and call the first turn function. If it's not the first turn, then we will go ahead and we will create a shot proof, with this shot being passed into the prepare shot proof function and whether or not it's a hit. And real quick, this was hit function. It's just looking at the place ships on your board and seeing whether or not the tile that was shot at previously was indeed a tile that held a ship or not. And then looking at the prepare shot proof function, again, the same idea here with when we're placing ships. We just go through and convert them to a form that is passable into the proof. So x coordinate is going to be remainder of the ship head divided by 10. We're going to get the y coordinate by dividing the ship head by 10 and rounding to the floor. And then z is gained from the orientation of the ship. And once we have this converted to a 2D array, we then pass this into the shot proof function along with the shot coordinates here and whether or not there was a hit, passing from these parameters. Looking at the shot proof function, we first start off by creating a ship hash. We showed this function before when we were placing our ships on the board for a board proof. We then check the hit. If it is a hit, or if the hit variable equates to true, then we will assign it 1. If not, then 0, just so it's a friendly input to the proof. So it has to be a U1 instead of a Boolean right now. We then flatten the board array to convert this to a 1D array. Again, a format readable by the proof. And then finally pass in that shot array to the ABI. And then we call the generate proof function, specifying it is a shot proof and the ABI is of the shot type. And then going back down to the take shot function, we take this proof, we load in all of the parameters, and then finally call the smart contract function turn. And that concludes looking at how proofs are integrated into a React app front end. So I think now we're going to hop in and show how we can generate these public, or these files that go in the public directory. So looking at the main repository, we have a file called generate frontend data. And in here, we want to specify the proofs we're going to generate those Acer and circuit buffer files for. We also want to specify a directory to write these files to. And lastly, we want to specify those Aztec npm packages we want to copy the WebAssembly files for. And here we specify the dependency name, and this is for the purposes of logging to see where we are in the process when we run a script to create these files. File is going to be the name of the file itself, and the path is going to be how to access that file within Node modules. So starting off, we first loop through all the proofs. We will access that Noir file at the specified directory and compile it. We will then grab the Acer from the compiled circuit, and using a function called serialize Acer to Brandenburg circuit imported from the Aztec Backend package, we will then have it in a form where we can get the circuit size from it. And to do that, all we have to do beforehand is initialize the Brandenburg WebAssembly class and then pass it into this get circuit function along with the serialized circuit. And this function is imported from the Brandenburg library. And then we check to see if the directory exists yet. If not, we'll make it, and then we will write those files to that directory down here for each proof. And then finally, we then look for the WebAssembly files we need to copy over, go to that specified path, and then copy them into that specified directory again. And that's pretty much it. We then go down to the package.json file, and we can see we have a script here called generate frontend files. So we'll go ahead, do yarn generate frontend files. You can see the circuit size right there. And boom. It's all been written to this directory deploy/frontend. And then all we have to do, if we want to copy these over to our front end, we would just do click shift to select all the files and then drag them over. There we go. And that concludes this video for integrating proofs into front ends. And this marks the end of the BattleZips-Noir series. Really hope the videos were helpful, no matter where you are in your ZK journey. And going forward, if you like to stay in touch, recommend reaching out to us at the Battlezips Discord. And if you have questions and would like to speak to the Noir team directly, reach out to the Aztec Discord. But that's going to wrap it up. Thanks so much for watching.